These colorful origami structures are actually robots, kind of. They're made of modular metamaterials, which act like passive, programmable robots, and their origami-inspired design can help them improve the world of engineering. Cool? Confusing. Let's break it down. Let's start with the name. Metamaterials is the fancy term scientists give materials that have been engineered to improve their design, application, and performance, so they can do things simple materials can't. An example for a simple material is cast iron. Cast iron is a pretty sturdy material, which can make it difficult to work with. Add carbon to it and it becomes steel, a metamaterial that is just as strong but way easier to bend than cast iron. And because metamaterials design can be easily manipulated, over the past few decades, engineers have developed shapes that can help improve things like their acoustics and flexibility, as well as their optical and mechanical properties. Enter this fun little thing, which may look fragile, but is actually capable of supporting walls. Developed by researchers at Princeton University, the design of this metamaterial was inspired by origami, and specifically the Kressling origami structures named after their creator. The Kressling origami are specifically engineered to be as foldable as possible. But even though these structures can bend and fold following their origami pattern, they're still rigid, meaning they can't twist or bend. That's why the Princeton researchers combined the origami-inspired design with something called chiral geometry. We call chiral all figures which have a mirror image but are not identical to it. The term's name comes from the Greek chir, which means hand, as the human hand is the best way to explain chiral figures. Even though our left and our right hands mirror each other, they're not identical. So because of the unique combination between origami design and chiral geometry, these metamaterial structures are pretty flexible. In one single movement, they can twist up to 90 degrees, shrink their height in half, and contract sideways by up to 25%. And remember when I said these origami structures both are and aren't robots? Well, they don't have electronics or motors inside, so they aren't technically robots, but they are referred to as robotic because, just like machines, they can autonomously perform complex tasks, including the shape-shifting we just mentioned, as well as modular assembly, and a thing called non-commutative state transitions, which simply means that if you twist the structure and then bend it, you'll get one result. But if you bend it first and then twist it, you'll end up with something completely different. And though all of this can sound rather dry, its potential real-life applications are anything but. The origami metamaterials can be used in fields as different from each other as robotics and construction. In construction, the metamaterials could improve thermoregulation systems, and they can help buildings or heating devices self-adjust to respond to temperature and airflow shifts. Just imagine a building with insulation that moves. And in robotics, well, do you remember Transformers? These metamaterials can help create robots that reconfigure themselves depending on the environment they're in and the task they need to perform. These are only two of the many possible applications of flexible metamaterials, and we can't wait to see what engineers do next. Until then, if you want more similar breakdowns and stories about science and tech, go to Mashable.com, follow us, or subscribe to our YouTube channel.